Our friend Joe McCann, aka Average Joe, has found an SAT math problem that is diabolically difficult, honestly, and I have found a solution that I think he will enjoy. But let's first hear from him what the problem is.
What is 10% of 470, with the options being 37, 47, 423, or 460? Now,
So the problem is to find the 10% of 470, or equivalently, find x such that 470 divided by 10 is x. But working with equations, polynomial equations with rational numbers, is much more complicated than working with Diophantine equations. So we can multiply through by 10 and get this equation. This is a polynomial equation with integer coefficients. That's a Diophantine equation that we can solve. 10x minus 470 is a Diophantine equation of degree 1, and therefore, by the Hasse-Minkowski theorem, this equation will have solutions if and only if it has real solutions and it has p-adic solutions for every p. So what we're going to use is p-adic analysis, where you're going to use p-adic numbers to find solutions for several p-adic fields so that we can compose those solutions together to find a solution over the integers. Notice that over the real numbers, there is a solution. We don't know what the solution is, of course, but that is a degree 1 polynomial over the reals, and those always have one real root, so we don't have to worry anymore about the real numbers. Let's find first a solution over the two adics using Hansen's lemma. What we need for that to get it started is to know what is a solution modulo 2 or modulo 4 and so on. So let's see what happens. Modulo 2, this is 0 is congruent to 0 modulo 2, so we don't get any information. Modulo 4, the equation reduces to 2x minus 2, and that gives me actually two solutions, 1 or 3 modulo 4. When I go modulo 8, I get again two solutions, 3 or 7 modulo 8, but notice that both of them reduce to 3. So that one was eliminated in this step. Similarly, modulo 16, the solutions are 7 or 15, which both reduce to 7, so the solution 3 modulo 8 gets eliminated, and so on. So you can keep building like this a solution in Q2. And as you go on, you see that the solution, an approximation or a p-adic expansion, a two-adic expansion of the solution is 1 mod 2, 3 mod 4, 7 mod 8, and etc. So this is one approximation, one two-adic approximation to the solution. Let's move on to the three-adics. Over the three-adics, the solution is 2 mod 3, 2 mod 9, 20 mod 27. So this is, again, a three-adic approximation of the solution, and that will be enough for our purposes. In Q5, in the 5-adics, we encounter similar issues as we found in Q2, but anyway, we can resolve those and find that the solution is has this 5-adic expansion, 2 mod 522 modulo 25, etc. Similarly, over the 7-adics, this is expansion, 5 mod 7, 47 mod 49, etc. So now, in summary, x is a real number. It has this expansion over the 2-adics, 3-adics, 5-adics, 7-adics, etc. And the problem now gives us 4 different options. Those are 4 integers, so it's enough to compute the solution modulo 840, because if I know it modulo 840, it will be one of those 4 numbers, and 840 is 8 times 3 times 5 times 7. So all I need to know is what is the solution x modulo 8, modulo 3, 5, and 7 to make up the solution modulo 840. To compute a solution modulo 840, what we do is use the Chinese remainder theorem, because we're looking for an integer that is 7 mod 8, 2 mod 3, 2 mod 5, 5 mod 7, and the Chinese remainder theorem assures me that there is a unique solution modulo the product of these moduli. So there is a solution modulo 840, and I will spare you the details of how I found the solution of the Chinese remainder theorem problem, but using these simpler problems, I can get that x is 7x1 plus 2x2 plus 2x3 plus 5x4 modulo 840, and if you simplify that number, that is 47 modulo 840, so the solution we were looking for is 47. 47 is 10% of 470.